Principle of organic chemistry. Can you recall which is the essential element in all organic compound? What is the unique property of carbon that makes organic chemistry a separate branch of chemistry? Which classes of organic compounds are often used in our daily diet? Introductions. Of all the elements, only carbon is able to form an immense array of compounds, ranging from methane having one carbon atom to deoxyribonucleic acid DNA with millions of carbon atoms. Crude oil is a complex mixture of compounds called hydrocarbons. The pharmaceutical industry is one of the most important chemical industries that provide us medicine, which are organic compounds. We need to study the organic compound for they are interesting in their own right and their functions are greatly important to life. Find out the structure of glucose, vanillin, camphor and paracetamol using internet. Mark the carbons atom present in them. Assign the hybridization states to each of the carbons and oxygen atom. Identify sigma and pi bond in this molecule. 14.2 Structure representation of organic molecule. Draw the structure formula of ethane. Draw electron dot structure of propane. In the previous standard, you learn how to write structure formulae and electron dot structures of hydrocarbon. Structure formula of molecule. Show all the constituents. Atom denoted with their symbol and all covalent bond. They are represented by a dash joining mutually bonded atom. For example, structural formula of methane is in the valence dot structure of molecule. The valence electron of all the atoms are shown as dot around them. Two dots drawn in between two atoms indicating one covalent bond between them. For example, the electron dot structures of methane is as shown here. Electron dot structures are called Lewis structure and dash formula represents simplified Lewis formula. Chemists have developed some more way to represent organic molecules fulfilling specific requirements. Condensed formula. The complete structure formula can be further simplified with hiding of some or all the covalent bond and indicating the number of identical groups attached to an atom by a subscript. The resulting formula of a compound is known as condensed formula. For example, condensed formula of ethane can be written as ethane CH3CH3 or CH3CH3, a bond line formula or a zigzag formula. In this representation of a molecule, symbol of a carbon and hydrogen atom are not written. The line representing carbon-carbon bonds are drawn in a zigzag manner, and terminal of the zigzag line represent methyl group. The intersection of line denote a carbon atom bonded to appropriate number of forgotons and set of hydrogen which satisfy the tetravalency of carbon atom. For example, propane is represented by the zigzag formula. However, the heteroatom or hydrogen atom bonded to heteroatoms are written clearly. For example, the bond line of formula C2H5OH is CH3CH2OH. Table 14.1 Representation of structure formula dash formula CH3 CH2 CH2 CH3 condensed formula is CH3 CH2 CH3 condensed formula B CH3 CH2 CH2 CH3 bond or zigzag formula which is CH3 CH2 CH2 CH3. Drawing the molecule in three dimensions. Most organic molecules have three-dimensional shapes. For different methods are used to represent the three-dimensional molecule on plain paper. Wedge formula. The three-dimensional view of molecules can be represented on a plain paper by representing the single bond using solid wedged, dashed, wedged, and normal lines. A solid wedged is used to represent a bond projecting up from the paper towards the reader. A dashed wedge is used to represent a bond going backward below the paper away from the reader. Normal line depict bond in the plane of the paper. For convenience, solid and dashed wedge are replaced by solid or bold and dashed lines. The normal line is the bond in the plane of paper. The wedged line is bond going below the paper, which is away from the reader, and the solid line is the bond projecting above the paper. That means the bond is projecting towards the reader. Fisher projections formula or a cross formula. In this representation, a three-dimensional molecule is projected on plane of a paper. A Fisher projection formula can be drawn by visualizing the molecule with its main carbon chain, vertical. Each carbon on vertical chain is represented by a cross. The convention is that the horizontal line of the cross represents bond projecting up from the carbon and vertical line represents the bond going below the carbon. Figure 14.2 illustrates the convenience of Fisher projection formula. Fisher projection cross formula is CCOH CHOH CH3. C wedge line is away from the reader, solid wedged is towards the reader. COH CH2OH CH2OH CH3. Fisher projection or cross formula. COH CHOH CHOH CH3 wedge formula. Fisher cross formula. Fisher projections formula is more commonly used in carbohydrate chemistry. Newman projections formula. In this method, projection of a three-dimensional molecule on the plane of the paper is drawn by visualizing the molecule by looking through a C single bond C. In such a case, the C single bond C is not visible. A convention is followed to represent the front carbon by a point and the rear carbon by a circle bond around it. The remaining three bonds at each of these two carbon are drawn like spokes of a wheel. Conventionally, three bonds at the front carbon are shown to radiate from the center of the circle, which is the front carbon, and three bonds at the rear carbons are shown to radiate from the circumference of the circles. Shown to representation of ethane CH3 molecule by these methods. Newman projection formula of ethane, sawhorse or andirons or perspectives formula. In this representation on C single bond single bond is represented by a long slanting line. The lower end of the line represents the front carbons and the upper end the rear carbon. The remaining three bonds at the two carbons are shown to radiate from the respective carbons. At the center C single bond C bond is drawn rather elongated. The bond radiating from the front and rear carbon do not intermingle. Figures show two sawhorse andirons or perspectives formula for ethanes. Sawhorse formula of ethanes. Try this, draw two Newman projection formula and two sawhorse formula for the propane molecules. Classification of organic compound. With so many different molecules to study, it is important to find a way of relating different structure of molecule to their chemical properties. This provides basis for classifying organic compounds. Organic compounds are broadly classified in two ways, on the basis of first carbon skeleton and secondary functional groups. Do you know? Molecular model figure 14.5 are used for an easier visualization of three-dimensional shape of organic molecule. Three types of molecular models are common. Framework model, it emphasizes the skeleton patterns of bond ignoring size of atom. Balls and sticks model. In this model, a ball represents an atom and stick a bond. Space filling models, it emphasizes on relative size of each atom. Bonds are not shown, it conveys volume occupied by each atom in the molecule. Nowadays, computer graphics can be used for molecular bond links. Framework models, ball stick model, space filling models, molecular models. Organic compound is classified into a cyclic or aliphatic open chain, and second is cyclic closed chain. The cyclic closed chain is classified into two types: homocyclic, carbocyclic, heterocyclic. Homocyclic, which is classified into a alicyclic aromatic. Aromatic is classified into benzenoid aromatics and non-benzenoid aromatics. Heterocyclic is classified into heterocyclic aromatic, heterocyclic non-aromatics. Classification based on carbon skeletons. Classification based on carbon skeleton. Try this. Construct a model of a propane CH3CH8 molecule which atoms are on the surface of the molecule, which atoms lie in the core of the molecule. The carbon atom bonded to each other lie in the core of an organic molecule and are described as the carbon skeleton of the molecule. It is the carbon skeleton of a molecule that decides its shapes and size. A variety of carbon skeletons are found in different organic compounds, and accordingly they are classified into various types as shown in figure 14.6. A cyclic or open chain compound. These are also known as aliphatic compounds. Molecules of this compound have chain of carbon atom. This may be straight chain formed by carbon atom bonded to one or two other carbons, or branched chain having at least one carbon bonded to three or four other carbons. Table 14.2 shows an example of a cyclic compound. A cyclic or aliphatic compound: propane and propyl alcohol, isobutane branched chain. Cyclic compound. These are compounds in which molecules are formed by joining atoms to form ring-like structure. The compound in which ring is made of only carbon atoms are known as homocyclic or carbocyclic compound. Carbon is an essential atom in any organic molecule. One or more hydrogen atoms are present in most of organic molecules. All other atoms are found in organic molecules are called heteroatoms. The cyclic compound in which the ring includes one or more heteroatom oxygen, nitrogen, sulfur are known as heterocyclic compound. Try this. Cyclohexane, piperidines, cyclopentanes, benzenes, pyrols. Observe the compound A to E. Identify the compound those contain a carbon of ring of carbon atom only. Identify the compound in which ring contain at least one atoms other than carbons. Alicyclic compounds. These are cyclic compounds exhibiting properties similar to those of aliphatic compounds. For example, cyclobutane, cyclohexane. See figure 14.7. Aromatic compounds. Aromatic compound has special stability. Aromatic compound containing benzene rings are known as benzene aromatics, while those not containing benzene rings are called non-benzene aromatics. For example, benzenes, tropanes, cyclobutane, cyclohexane, alicyclic compounds. Naphthalenes, phenols are benzenoids aromatic compounds. Tropone, non-benzene aromatics compounds. These are the carbocyclic compounds. 14.8 illustrates some heterocyclic compound. Heterocyclic aromatic compound: furan, typhoon, pyridines, pyrols. Heterocyclic non-aromatic compounds: tetrahydrofuran, piperidine, 4H pyran, THF. Classification based on functional groups. Can you tell? Consider the following reaction: 2 moles of 2 moles of propanol react with 2 moles of sodium to give 2 moles of CH3, CH2, CH2ONA plus H2. Compare the structure of the substrate, propanol, with that of the product, sodium propoxides. Which part of the substrate, the carbon skeletons or other OH groups, has undergone a change during the reactions? A part of a organic molecule which undergoes change as a result of reaction is called functional group. In the above illustration, OH is a functional group present in propanol. Inspection of a group structure of various organic compounds tells us that there are a large variety of functional groups present in them. The second method of classification of organic compounds is based on the nature of functional groups present. The resulting individual class is called a family named after the constituent functional group. For example, family of alcohol, family of halogen derivative. Table 14.3 shows some common functional group with their names and bond structure and examples. Homologous series. A family of functional group in turn comprise different homologous series. A series of compounds of the same family in which each member has the same type of carbon skeleton and functional groups and differ from the next member by constant difference of one methylene group CH CH2 in a molecular structure formula is called as homologous series. An individual member of homologous series is called homologs. All member or homolog of such series are represented by the same general formula. The member of particular homolog series possess similar chemical property, those very gradual in their physical properties, namely melting point, boiling point, density, solubility, etc. Table 14.4 illustrates this with the help of homologous series of straight chain aldehyde having general formula CnH2nO. Do you know aliphatic compounds are named so because of their attraction towards fats? Aromatic compounds are named so because some of these compounds discovered in early 19th century possess aroma. Name of the family or functional group. Structure of the functional group. Example. Halide. X. CH3Br. Methyl bromide. Cyanide or nitride. C triple bond N. CH3CN. Methyl cyanide or acetonitriles. Isocyanide. Dash N minus triple bond C plus CH3NC methyl isocyanide. Nitro compound or nitro groups. N double bond O plus O minus. CH3NO2 nitromethanes. Alcohol dash OH. CH3OH methyl alcohol. Phenol AR dash OH. C6H5OH phenol. Primary amine dash NH2. CH3NH2 methylamine. Secondary amine dash NH dash CH3 dash NH dash CH3 dimethylamine. Tetramine dash N dash dash CH3N trimethylamine ethers. C dash C dash 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 O dash C dash 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 dimethyl ether CH3O CH3 aldehyde dash C double bond O dash H acid aldehyde CH3CHO ketone dash C double bond O dash is acetone CH3C double bond O CH3 carboxylic acid dash C double bond O dash OH CH3COH acetic acid ester C double bond O dash CH3C double bond O C2H5 ethyl acetate amide C dash C double bond O NH2 CH3CONH2 acid amide secondary amide dash C double bond O NH dash CH3 C double bond O NHCH3 tertiary amide is dash C double bond O dash N dash dash CH3 C double bond O NCH3 to NN dimethylacetamide acid anhydride dash C double bond O O C double bond O dash ACH3 C double bond O O C double bond O CH3 acid anhydride acyl chloride dash C double bond O dash Cl CH3 C double bond O Cl acid chloride acetyl chloride sulfuric acid is dash S double bond O dash OH dash H C6H5SO3H benzene sulfonic acid alkene or olefin is dash dash C double bond O C dash dash CH2 double bond CH2 ethylene Alkyne dash C triple bond C dash CH triple bond CH acetylene. Alkane no functional group CH3 dash CH3 ethanes. Problem 14.1. Alkane constitute a homologous series of straight chain saturated hydrocarbon. Write down the structural formula of the first five homologue of this series. Write their molecular formula and deduce the general formula of such homologue series. Solution. The first five homologue are generated by adding 1 dash CH2 dash at a time, starting with first homologue CH4. CH4 first homologue. Add CH2 CH3 dash CH3 second homologue. Add CH2 CH3 CH2 CH3 third homologue. Add CH2 CH3 CH2 CH2 CH3 fourth homologue. Add CH3 CH3 CH2 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 CH3 fifth homologue. By counting carbon and hydrogen atoms in the 5 homologue, we get their formula as CH4, C2H6, C3H8, C4H10 and C5H12. Comparing this molecular formula, the following general formula is deduced: CnH2n plus 2. Write down the structure formula of A, the third higher, and B, the second lower homologue of CH3CH2COH. Solutions. A structural formula of third higher homologue is obtained by adding 3 CH2 units to the carbon chain of given structure. CH3CH2COH, add 3 CH2 units. CH3CH2CH2CH2CH2COH, third higher homologue. B. Structure formula of second lower homologue is obtained by removing 2 CH2 units from the carbon chain of the given structure. CH3CH2COH, remove 2 CH2 units HCOH. Remember, the saturated sp3 carbon in a molecule are labeled as primary, secondary, tertiary, and quaternary accordance with the number of other carbon bonded to it by single bonds. Primary carbon first degree is bonded to only one other carbon. For example, both the carbon in ethane CH3CH3. Secondary carbon 2 degrees bonded to two other carbon. For example, the middle carbons propane CH3CH2CH3. Tertiary carbon third degree is bonded to three other carbons. For example, the middle carbon is isobutane CH3CH3CH2. The quaternary carbons 4 degrees bonded to four other carbon. For example, the middle carbon in neopentane is CCH3 4.